It is a great pleasure to give the keynote for the refactoring workshop, as it is very close to my heart. In 2019, I had the privilege to organize the last in-person refactoring workshop in Montreal, and as you can see from the picture, it was a great success. Not just because everyone is smiling, but mainly because many great ideas and collaborations were born in this edition of the workshop. If somebody asks me what have I done for refactoring, I would answer simply with two words: Deodorant and RefactoringMiner. So Deodorant is a refactoring recommendation tool that I started developing as a PhD student. Obviously, throughout the years, there were many newer techniques that had better precision and recall. However, I'm very proud of this work because it kept its promise, which was to support all activities of the refactoring process. The second tool is RefactoringMiner, and as you can understand from the name, it's a tool that can detect refactorings in the commit history of projects. Now, in the first part of my talk, I will focus on the story behind RefactoringMiner. The story started right after I graduated from my PhD under the supervision of Alexander Hadjigeorgiou, who was a great mentor and shaped me as a researcher and as a personality. So then I moved to Edmonton and the University of Alberta, where I did a postdoc under the supervision of Eleni Stroulia. As you might know, Eleni Stroulia, together with Zheng Chang, they developed UML Diff and JDevan, which was the state-of-the-art refactoring detection tool back in the mid-2000s. This tool was great, but it was a little bit difficult to use, as it required to import two versions of a project inside Eclipse, build them without any compilation errors, and also it had a database as the backend, which was quite challenging to set up. So when I joined Eleni's lab, Eleni had a master student, Fabio Rocha, who was working on developing JDevan as a web service so that it's easier to use. Fabio had developed a lot of tooling and infrastructure in order to process SVN commits and also being able to create from commits Eclipse projects. So this gave me a lot of inspiration to start working on a refactoring detection tool that is able to process commits. And with this version of the tool, we published our first related work on CASCON 2013, which I call version 0.0. So in this work, most ideas for the detection of refactoring were inspired from UML Diff. The structure of the method bodies was completely ignored. The only information we're storing about method bodies was method calls and field accesses. And as you can see from the table on the right, most refactorings were detected based on signature matching. In the paper, we provided only precision, which was very high, but this was easily explained because the rules were very strict, and as a result, there were very few false positives. And our evaluation included only 3 systems. Despite all these limitations, this work had a very interesting research question, which was, what is the purpose of the applied refactorings? To investigate this question, we manually examined all detected refactorings in these 3 systems and came up with a catalog of motivations explaining the reasons that the developers applied these refactorings. Here you can see an overview of the catalogs for extract method and inheritance-related refactorings. As you can see, the motivations are related to code smells, extending the code, backward compatibility, and refining the abstraction level. So after I finished my postdoc at the University of Alberta, I moved to Montreal and Concordia University to start as an assistant professor. However, I didn't work again on this research problem of refactoring detection. And what was the reason for that? The reason was that RefFinder, which was back then the state-of-the-art refactoring detection tool, had a very high precision and recall reported in the paper, which was 74% precision and 96% recall. So this very high recall number made me very hesitant to work on this topic because I thought it was impossible to further improve. However, if you read more carefully the paper, you will see that the authors constructed their oracle using their own tool with two different similarity thresholds. And this is a big bias for the Oracle, because it doesn't mean that even using different thresholds, the tool is able to detect all possible refactorings done in the history of projects. So the first lesson that we can learn is that we should not be intimidated by super results that we read in the papers, and we should always question these results. There is always space to further improve. So as I said, I stopped working completely on this refactoring mining topic until one day I received this email from Danilo Silva and his supervisor Marco Tullio Valente. I already knew Danilo because I was the examiner for his master thesis, and basically in his email he's asking if it is possible to share the source code of the tool that we used in the CASCOM paper I talked to you about before. Obviously, I was very happy to share the code. However, this code luckily was stored in an external hard drive. I didn't make any repository for it. And it was in this compressed file named xmi-diff. If you wonder why the name xmi appears there, is because the tool back then was also possible to compare UML class diagrams with source code in order to check if there is a drift between the original design and the actual implementation of the code. And the UML class diagrams are exported in a file format called XMI. So the second lesson we can learn is that we should always make our code and data available in a repository. And the reason is that it is not possible to know what this code and this tool can enable in the future. And at this point, I would like to talk to you about some open science initiatives. So here, as you can see in this chart, we see that the majority of the software engineering and programming language conferences have introduced an artifact evaluation track. So all accepted papers can submit a separate artifact submission that is evaluated by an independent committee. And according to some criteria, the paper gets some badges. And also I would like to mention that this year, ICSI 2022, had a mandatory field where the authors had to explain and provide the data availability. They have to give a link to their dataset or tools, or explain why this was not available, and this was a mandatory field. So this shows that our science is going to the right direction, because it's not acceptable to have papers published that cannot be replicated. So after a while, Danilo and Marco came back to me and said, okay, let's do an empirical study about refactoring. We discussed about it and I said, of course, but I think we should start the question about why we refactor, because I was not satisfied with the way I did it back in the CASCOM work. At this point, I would like to thank and acknowledge Danilo and Marco, because without their bugging me, the whole refactoring mining research would never have started. So I'm deeply thankful to them about all this collaboration and the work that came after it. So we started working for an ICSI paper that we submitted in 2016, and this can be considered as the version 0.1 of RefactoringMiner. So in this work, Danilo developed the API of RefactoringMiner. He developed a lot of tooling for checking out and parsing Git commits. He developed an infrastructure for monitoring GitHub projects for refactoring activity, and also for automatically generating emails to contact developers in the case where we were finding some refactorings in the commits. And finally, he also created a web application that could support performing a thematic analysis on the collected responses from the developers in order to come up with the motivation themes. So we followed the Firehouse interview method, where we monitor 124 GitHub projects between June and August 2015. We sent in total 465 emails and we received 195 responses, which is a 42% response rate. In addition, we had 27 commits for which we already had the reason behind the refactoring in the commit message. And after doing the thematic analysis, we compiled a catalog of 44 distinct motivations for 12 different refactoring types. So the output of this work was a catalog of motivations. So here you can see the motivations behind the extract method. This refactoring type has the most diverse motivations. We found 11 different motivations for applying this refactoring. And also we made available the artifact, which included all instances of refactorings that we found, along with the responses of the developers, the motivation tags that resulted after our labeling, and also some answers related to the usage of refactoring tools, whether refactoring was applied manually or with the use of a tool, and if it was applied manually, what was the reason for that. So we're very excited about this work. However, when we received the reviewer comments, we found out that the paper was rejected. And actually one of the reviewers had the wrong claim, was saying that we used RefFinder as a tool, which is known to have very poor precision and recall. And that although we tried to eliminate false positives by manual inspection, we didn't do anything related to the low recall of the tool. So this was obviously a false claim because we were not using RefFinder, we had developed our own tool. So we contacted the program chairs to let them know about this mistake. In turn, they contacted the reviewer who admitted the mistake. However, still the paper was rejected because there were some other issues about that. Okay, after this disappointment, we learned this lesson that even ICSI reviewers can make mistakes. However, we shouldn't get disappointed. We should always try to improve, advance the current state of the art in the evaluation, and resubmit. So we attempted to resubmit this work again to FSC in 2016. One of the changes that we made is that we renamed the tool in the paper from RefDetector to RefactoringMiner in order to avoid any other misunderstandings. So this was the time that RefactoringMiner got its official name. And we also, of course, addressed most of the reviewers' comments. So after a while, we got the results, the paper was accepted, and a few months later, we also learned that the paper received not just one, but 2 awards, a Distinguished Paper Award and a Distinguished Artifact Award. Obviously, we were very excited about this recognition of our hard work, and we started thinking about what would be the next steps. Danilo and Marco were already started working on their own tool, which eventually became RefDiff and was published in MSR 17. So there was some discussion in order to make a common paper that we would compare RefDiff with RefactoringMiner. However, this RefactoringMiner didn't have any of my ideas, and I was not 100% satisfied with the way it was working. So there was a lot of space of improvement, and I needed time in order to implement these ideas and test these ideas. So at this point, our paths separated, and Danilo and Marco continued working on RefDiff, while I started with my team working on a rebirth of RefactoringMiner. So this brings us to the myth of Hercules related to the crossroads that he faced. So here you can see Hercules that is in front of 2 paths. On the right, there is Vice. This is a young and attractive woman that is pointing Hercules on a path that is downslope, well paved, very easy to go through, and it leads to immediate success and happiness. However, as we can see in the background, in the long term there is some disaster coming. Now on the right side we see Virtue. Virtue is like an old, exhausted lady that is pointing Hercules to a mountain that is very hard to climb, very steep mountain. However, if you work hard, we can see that justice can be made that can help you climb this mountain. And after achieving climbing this mountain, you can reach eternal honor. So the Hercules crossroads actually resemble what can also happen in science. We can always take the easy path and publish first and receive the immediate benefits of having the first publication in a field. However, giving the best solution requires way more hard work, but eventually it can lead to a long-term impact. So now this leads to the first version of RefactoringMiner 1.0 that was submitted to ICSI in 2018. So what were the limitations of previous approaches? The first limitation was that they were depending on similarity thresholds. However, a lot of research has shown that these thresholds cannot be universal and cannot work well for every project, as projects have very different characteristics and need different calibrations. The second limitation is that especially before RefDiff, all tools were depending on built versions of projects in order to detect refactorings. However, as we have seen in other studies, only a small percentage of the change history can be successfully compiled. And this is a big blocker for doing mining studies over the commit history. And the final limitation is that all previous tools, they used unreliable oracles for evaluating precision and recall. So these oracles were either incomplete because refactorings were found in release notes or commit messages, which we know developers do not document every refactoring that they do there. Either the oracles were biased because a single tool was applied with two different similarity thresholds in order to make the oracle. And we have cases of artificial oracles where, for example, some students had applied some random refactorings on projects. However, although in this way you can accurately compute the recall of your tool, these refactorings are not representative of real refactorings because, first of all, they do not meet any real requirements, and second, they don't come with the noise of overlapping changes that usually happens in commits. So we decided we will develop an approach that the thresholds will be banned, so no thresholds will be used there. So how we achieve this, I will show you through an example. So think now that we have this method, and in the next commit, you see that there are some changes happening in the methods. First of all, the return type of the method is changing from an array of address to a list of address. In addition, we see that a new parameter is added to parameterize the port's value. And then we see that this try-catch block is extracted into another method in order to be reused. And also all the values, the arguments that are passed in order to create the address object are parameterized through the parameters host and port. Now, if we had an approach to compare the similarity of statements, we would see that these two statements that I highlight here that create the address object, that were originally the same statement, have become textually different. So if you compute the textual similarity of these two statements with, let's say, Levenstein distance or bigram similarity, you will get a similarity of 30%, which is very low. This means you would need a very low threshold to match these statements that would introduce other problems in having wrong statement matches. So we address this problem by applying three techniques. The first technique is called abstraction, which means basically when you have assignment statements or return statements, we compare only the expression that follows the assignment or that follows the return statement. In that case, it would be the creation of the address object. The second technique we applied is called argumentization, which basically means when we have extract method or inline method refactorings, we replace the parameters with the actual arguments passed when calling the extracted method. As you can see, the two statements are becoming more and more similar. However, they still have one difference, which is this ports variable. So the third technique that we apply is that we perform all possible AST node replacements for the nodes that are different between the two statements until we succeed to make the two statements identical. So here, by replacing ports field with the port's local variable, we can make them having a 100% textual similarity, and thus we can match these two statements without using any kind of similarity threshold, just by taking advantage of the refactoring mechanics. So to tackle the third challenge of building a reliable oracle, I had the great help of my students. Matin, who was a master's student back then, Lale was a postdoc in the group, and Davud was a PhD student. So what we did is that we used the dataset from the Why We Refactor paper that I talked to you before, which included 538 commits from 185 open source projects. We executed both available tools at the time that could work on commits, and this was RTool and refdiff. We converted the output of the tools to the same format, and we manually validated all refactoring instances, which were around 4,000, out of which 3,200 were true positives and 900 were false positives. The validation process was labor intensive and involved 3 validators for a period of 3 months. And to compute recall, we considered the union of the true positives reported by both tools as the ground truth. The idea behind this is that as the number of the tools increases, and especially if the refactoring detection tools use different methods for detecting the refactorings, the ground truth will become more complete. We also created a web app to help us in the validation process. So here you can see a refactoring instance, extract method refactoring instance. You can see all the tools that detect it. We had links that lead directly to the exact line where the refactorings happened. And there we can see different validation options, as well check who participated in the validation. And also we were able to enter some free text comments for our communication. So in comparison with refdiff, we can see that RefactoringMiner achieved almost 20% improvement in precision. However, still the recall of the tools were very similar. So if I want to do a retrospective about this work, I can say that our solution was still far from perfect. And this was because there was a lot of time pressure. It was very urgent to establish RefactoringMiner with a publication after refdiff was already established. We had the ICSI deadline that was on August 25th, but we even had an even more strict deadline, which was the birth of our daughter Sophia, which was expected on August 15th. So we really had the pressure to finish all this work at least 1 week before Sophia's birth. So despite working over 1 year on this paper, there was still a lot of space for improvement. And one more problem that I faced is that the entire team graduated after this work. So at some point I was left alone working on this project. So this leads to the next version of RefactoringMiner, which is the most mature version of the tool. In this work, we added support for more replacements types, as you can see in table 5. And this actually increased the number of statements that we could match. We also added support for 20 new sub-method level refactoring types. That means refactorings taking place inside the body of a method, such as variable renames and so on. We also supported nested refactoring detection. Imagine having a method extracted from another extracted method. We also used refactoring inference. The RefactoringMiner had an inherent limitation that it couldn't find refactorings for methods that didn't have a body, such as abstract method or interface methods. So in that case, we used the information collected from methods overriding these abstract methods in order to infer refactorings in the signature of the abstract methods. And finally, we also improved the matching of method calls to method declarations with argument type inference. That means understanding the type of a parameter based on the actual argument passed when calling an extracting method or an inline method. Then, with the help of Ameya Ketkar, who joined our group between September 2019 and December 2019, we tried to build an even more reliable oracle. So we executed all available tools at the time. That was 2 versions of RefactoringMiner, 3 versions of refdiff, and 1 version of Gumtree diff, which is an abstract syntax tree diff tool. We converted the output of the tools to the same format, and we validated over 5,800 new unique refactoring instances, out of which 4,000 were true positives and around 1,800 were false positives. And we finally built an oracle that had over 7,000 true positives for 40 different refactoring types, and 72% of these instances were detected by 2 or more tools, which gives more reliability to this oracle. Now if we go to the precision and recall results, we can see that compared to the previous version of RefactoringMiner, we have a 3% improvement in precision. However, the big improvement is in recall, which is over 13%. And then compared to the latest version of RefDiff, we can see that we have like a 6% higher precision, but the big difference again is in the recall, which is almost 20% better. In addition, we developed some refactoring detection rules based on the output of Gumtree diff in order to find refactorings within the body of methods, such as renaming variables, parameters, fields, changes in return types, changes in variable types, and so on. And as you can see in the final results, we had an impressive improvement over Gumtree. So the improvement in precision is 39%, while the improvement in recall is 30%. Currently, we're working towards version 2.2, which is the most advanced version at this point. Just to give you one feature that it supports the detection of loops and if statements converted to the Stream API for reads and filter, as you can see in this example. So right now it supports 85 different refactoring types. There are 10,900 validated true posits in the Oracle. The precision is reaching almost perfection, 99.7%. The recall is 97%. And it is the most tested and reliable version we have. It has been tested on over 200,000 commits without having a single exception. And there are also now many independent studies that confirm that this tool has the best precision. So based on our experience, what it takes to make a reliable and usable tool? So at minimum, it takes 5 years of research and development. It needs extensive testing. Right now, we have a test suite that runs all commits in our Oracle, and there is no code committed if it doesn't improve precision or recall, or at least keeps it at the same level. We have very detailed documentation. We have a README file in our GitHub project with API code snippets and also help guidelines in order to run the tool in command line mode. We are supporting our users. We have over 200 issues that were resolved in our issue tracker. We have a stable project leader. I noticed throughout the years that many projects die because they were just run from a student who graduated and there is no one to continue supporting them. So it's very important to have a stable leader in the project. And also I had a great team of people that I collaborated with and really made the difference in improving this tool. In the second part of my talk, I will discuss about the promises of refactoring mining. And I will use some quotes from the original Refactoring Miner paper about the potential applications of refactoring mining, along with some papers as examples that fulfill these promises. The first promise was that refactoring mining can help researchers to replicate existing empirical studies and refute or confirm previously held beliefs. Obviously, there are many empirical studies that were done about refactoring. However, I would like to focus on two of them because they were giving a bad name to refactoring, and I always thought that this was a bit unfair. So the first study on the left investigated the relationship of refactorings with bugs, and it found that 15% of the bugs are actually induced by refactoring. Moreover, if we're talking about inheritance-related refactoring, this percentage increases to 40%. So this means inheritance-related refactorings introduce more bugs than other refactorings. On the right, we see a study that investigated the relationship of refactoring with regression testing. And in particular, this work found that 38% of the failed tests involve some refactoring. Obviously, both papers give the message that refactoring has very negative impacts on maintainability, as in it introduces bugs and also it leads to test failures. However, both studies had some serious threats to their validity. Both of these studies relied on RefFinder, which at the time was the state-of-the-art refactoring mining tool. Later on, independent studies have shown that RefFinder had quite low precision and recall. Soares and his colleagues in 2013 computed a precision of 35% for RefFinder and an recall of 24%. Later on, Kadar and his colleagues in 2016 computed a precision of 27% for RefFinder. Here I just want to remind you that the original RefFinder paper was claiming a precision of 74% and 96% recall. So we can see there is a huge gap between the results reported by the authors of RefFinder and the independent studies. Now, both of the studies, because they were using RefFinder, they collected refactoring information at release level. This means between two versions of a software system. And this led to perform a very coarse-grained analysis that in turn led to some strong and unsafe assumptions. Both of these studies were later on replicated by these two new studies that used RefactoringMiner as the mining tool. As a result, they were able to collect refactoring information at a very fine-grained level, because RefactoringMiner not only gives you the exact commit where the refactoring took place, but also the exact line numbers involving the refactorings. And in addition, both studies did a very extensive qualitative evaluation in order to validate their findings. Now, in the study on the left, the authors found that in a sample of 384 commits where the SSZ algorithm was blaming refactoring for the introduction of the bugs, they found that 62% of these bugs were actually unrelated to refactoring. Now, the study on the right found that only 2.5% of refactorings actually break tests, and these are some specific refactoring types related to the signature of the methods, such as adding parameters or changing the return type. So here we can see that using a more accurate tool and having a better experiment design can actually lead to completely different results. An important lesson that we can learn here is that when we are developing a tool, this comes with a very huge responsibility for the authors of the tools. This is because this tool can be later on used to conduct empirical studies or build other tools upon it. So this means we should go above and beyond when evaluating its accuracy. We should make sure that we are extended all our capacity when evaluating the accuracy of such tools. The second promise is that RefactoringMiner can actually be used to reduce the noise created by refactorings and significantly improve the accuracy of other tools. So here I would like to talk about two works that took some existing techniques and made them refactoring aware. The first one is a refactoring aware version of the SSZ algorithm. So this is an algorithm that actually finds the commits that introduce the bug. And they found that the refactoring aware version improved the percentage of valid bug introducing lines by 8% over their previous approach, while it also improved the median percentage of valid bug introducing lines per bug fix by 15% over the previous approach. On the right, we see IntelliMerge. IntelliMerge is a refactoring-aware merging tool, and according to the experiments of the authors, they found that it reduced the number of merge conflicts by 59% over Git merge, which is the standard merging tool used by developers, and by 12% over JFST merge, which is the state-of-the-art structural merging tool. So here a lesson that we can learn is that if we make existing code evolution analysis techniques refactoring aware, we can significantly improve their accuracy. The third promise is that the oracle that we created of the true refactorings from 538 commits across 185 projects provides an invaluable resource for validating novel refactoring tools and for comparing existing approaches. So here I would like to discuss two tools, namely RefDiff 2.0 and RefDetect, that followed the first version of RefactoringMiner. Both of these tools are multi-language tools. That means they're language agnostic and they have a technique that can be applied in many different languages. Both of these papers, they used our own oracle in order to compute the precision and recall in Java projects, and also of course compare it with the RefactoringMiner tool and other tools. The fourth promise is that refactoring mining can enable online refactoring detection on partial input when a developer inspects a code diff to review a change or tries to understand code evolution selectively. So here I would like to focus your attention on having partial input. That means having only part of the files to perform the refactoring detection, and also having a selective evolution. That means detect refactorings and changes specifically on a program element of our interest. The current state-of-the-art work on method tracking is CodeSovel. This is a tool that can quickly produce the complete and accurate change history for 90% of the methods, and this history includes 97% of all method changes. This tool is partially refactoring aware. This means it supports method signature changes, it supports method moves, and it supports also file renames and moves. In order to track a program element, it uses thresholds when comparing, let's say, two methods, and these thresholds were calibrated on a training set of 100 methods. It has, however, one limitation. It mismatches methods from which a significant part of their body has been extracted. So this means that it will match an extracted method with the original one if over 70% of its body has been extracted to this new method. On the other hand, it is ultra fast. It takes less than 2 seconds to fetch the entire change history of a method. So together with my master student Mehran Jodavi, we tried to tackle the following challenge. How can we take advantage of RefactoringMiner's high accuracy in a way that is not so computationally expensive? And the solution that we came up with is to do partial and incremental commit analysis based on the location of the track program elements. So this means we execute RefactoringMiner in some rounds, and in the first round we give the minimum possible input to our tool. This is the file containing the track program element in the child and the parent commit. So at minimum we can give 2 files. If we're not able to track the program element with this minimum input, we keep increasing the number of files given as input to RefactoringMiner until we track the file or until we find that this program element was introduced in this commit. Here are the results of the experiments we did. Now, for method tracking at commit level, that means finding all the commits where a change happened, we improved the precision over CodeSovel by 7.5% and the recall by 3.7%. While at change level, that means reporting the exact changes that happened in each commit, we improved the precision by 9% over CodeSovel and the recall by 6%. Also, we are the first tool of its kind to support variable tracking with a very high accuracy. So at commit level, we achieve a precision and recall over 98%, while at change level, we achieve a precision and recall over 97%. On the right, you can see 2 volume plots with the execution time distribution of the 2 tools. So on the far right, you can see the CodeSovel execution time. On median, it takes 2 seconds to extract the entire change history for a method, while CodeTracker, our tool, takes 3.5 seconds on median to extract the entire commit history of a method. So although our tool is slower than CodeSovel, as you can see, it is more accurate, and still the execution time is in the same order of magnitude. The 5th promise is that we can integrate refactoring mining with diff and code review tools in order to raise the level of abstraction for code changes originating from refactorings, and thus help developers to better understand the code evolution. The work that I would like to discuss related to this promise is Smart Commit. So Smart Commit is a technique that can decompose a composite commit into distinct activities, and it achieves a median accuracy between 71 to 84% when decomposing composite commits without the involvement of developers. The way the authors achieve this result is by introducing the div hang graph. In this graph, the nodes represent div hangs, while there are 4 different kinds of links connecting these nodes. We have hard links that represent syntactic constraints between the AST nodes. We have soft links that represent repetitive change patterns. We have refactoring links that represent edits in different locations which, however, originate from the same refactoring. And finally, we have cosmetic links that represent changes in comments and reformatting. Now, by computing the weights over these links and by partitioning the graph, the developers can find distinct activities in the commits and thus decompose the commit. The sixth and last promise is that refactoring mining can be used to automatically document refactoring operations at commit level in order to provide a more detailed description of the applied changes in the commit message. The idea here is to apply refactoring detection before even the changes are committed to a repository in order to enhance the commit message with some information related to refactoring. However, the authors of the interactive refactoring documentation bot went one step further by associating changes in design quality attributes with specific refactoring operations. So their approach works in the following way. Assuming we have a pull request, first they clone the project, and then they calculate some design quality metrics for specific classes in the pull request before and after the pull request. Next, they extract the refactorings that were applied in the pull request. And finally, they associate the changes in the values of the design quality attributes with some specific refactoring operations that were applied in the same files. Below you can see a generated pull request message where the changes in the quality attributes on specific files are connected with some refactorings that were applied on the same files. In the third and last part of my talk, I will discuss about future research directions in refactoring mining. The first research opportunity is to use mining for learning some commonly applied changes. In many cases, developers perform the same changes in different projects. With mining, we can detect these changes and group them into frequently applied change patterns, which can be automatically applied when a developer needs them in another project. A perfect example of such repetitive changes are type changes or API migrations, if you like. Here we can see an example from Project Undertow where the developer changes the type file to path. This type changes causes in turn changes in API calls. For example, here we can see that in order to create the files final target and temp target, the developer was calling the file constructor before. However, after the commit, the method resolve is called instead to get the corresponding path objects. Moreover, we can see that the initial type change from file to path is causing some cascading type changes. For instance, the type of variable temp has to change from file output stream to output stream, and the stream is no longer created by calling the file output stream constructor, but rather by calling the new output stream method declared in the class files. In the following lines, we see more API call changes caused by the initial type change from file to path. Obviously, such API migrations are type consuming and require a lot of effort from the developer. The developer has to study the documentation of the source and target types and find a mapping between the source and target type APIs. The same should be done for the cascading type changes too. RefactoringMiner detects such type changes and also returns all statement mappings that reference the variable whose type changed, along with the API changes as AST node replacements. Now, in his PhD work, Ameya Ketkar has developed a technique and tool that can automatically generate rewrite rules from the type change information collected by RefactoringMiner. For example, from the first two type changes in lines 122 and 123, the following rewrite rule can be inferred. In this rule, the code that is highlighted in white fonts is fixed, while the code that is highlighted in green corresponds to template variables that can have any value. The important thing here is that the first argument from the file creation, variable v0, becomes the expression through which the resolve method will be called. Furthermore, from the cascading type change in line 126, another rewrite rule is inferred. Now these rules can be combined to automatically migrate composite API calls as the ones shown here. By applying both rewrite rules above, we can automatically rewrite the statement as follows. Ameya, along with Oleg Smirnov from JetBrains Research, they developed a plugin for IntelliJ that can perform automatically type changes, and I will show you a short demo now. So the developer selects the type to change, and from a pop-up menu, he can select the target type, in this case path, and also the scope that the type change will be applied. The tool automatically performs the migration for the developer, and here we will see now the changes that it performed. As you can see, all statements referring to variable file has been updated to use the appropriate APIs. The second research direction is to use refactoring mining for improving refactoring recommendation tools. Refactoring recommendation was a popular research topic in the previous decade. So some may think that what can be done in this area was already done. I will try to convince you for the opposite. Together with my master student Sadek, we conducted a large-scale empirical study about the motivations of developers behind the refactorings they apply. We call this study Why We Refactor++. For this study, we developed detection rules for the extract method motivations as recorded in the Why We Refactor study published in FSC in 2016. We optimized these detection rules based on the Why We Refactor dataset. This is a very reliable dataset as the motivation is given by the developers who applied the refactorings themselves. Then we validated the accuracy of the detection rules based on the Pantuchina-Tosem 2020 dataset, in which the authors inspected pull requests with refactoring operations and labeled their motivations. In total, we collected the motivations for 346,000 extract method instances that were found in 133,000 commits of 325 open source projects. On the right, you see the motivation rankings from the Why We Refactor FSC 2016 paper. On the left, you see the motivation rankings from our own study. Although there are some changes in the two rankings, we can observe that the top 5 motivations are common in both studies. So we studied the literature to find refactoring recommendation tools supporting the top 5 motivations. For the top motivation, which is extracting a method in order to reuse it somewhere else, we didn't find any tool supporting it. For the second motivation, which is extracting a method to eliminate code duplication, we found at least 5 refactoring recommendation tools supporting it. For the third motivation, which is extracting a method to make easier the implementation of a bug fix or a feature, we just found one tool, FRefactor, that supports it. For the fourth motivation, which is extracting a method to decompose a long and complex method, we found at least 4 refactoring recommendation tools supporting it. Finally, for the fifth motivation, which is extracting a method to provide the same functionality with an alternative signature, we didn't find any tool supporting it. So there is clearly limited to no support at all for three major motivations driving the application of extract method refactorings. Using our motivation detection tool, we can study the characteristics of the refactorings belonging in these motivation groups and try to develop recommendation tools targeting these specific motivations and their characteristics. The third and last research direction is mining for improving accuracy. And this is essential for refactoring mining, especially now that there are tools supporting more programming languages, such as Python and JavaScript, for which we don't have reliable oracles. So I will talk about community efforts to build reliable benchmarks and oracles in other research areas, and how we can be inspired from them. The software testing community has created the JUnit generation benchmarking infrastructure in order to standardize the evaluation and comparison process of unit test generators in 8 unit testing tool competitions that you see in the table, which were co-located with the search-based software testing workshop. The software defect analysis community has recently published a 48-author paper with a corpus of manually validated bug fixing commits covering over 2,000 bugs from 28 projects. Each line has been independently labeled by 4 participants and has been annotated with a type of change. For example, whether the change modifies the source code to correct the problem causing the bug, or whether the change is a whitespace or documentation change, whether a change is a refactoring, whether a change is a test modification, or whether a different type of improvement that is unrelated to the bug fix. So my message is that making better refactoring mining tools is a community effort, and some actions that we could take towards this direction is to host mining competitions in the workshop, work on community-created benchmarks, and also make hackathons for improving our refactoring mining tools. Finally, I would like to show you some links to projects related to RefactoringMiner, some of which I mentioned in my talk. Thank you very much for your attention. I'm very happy to take your questions.